Hello, my name is Sven Breitkopf from Active Fiber Systems, and I would like to present our newest results on a long-term stable 120 watt fiber CPA system with 1.3 gigawatts of peak power at 2 micrometer central wavelength. And first of all, why do you need this? So the entire electromagnetic spectrum is very interesting for different applications. And if you want to address this range, you have to start somewhere, and applications can typically be enabled by wavelength and flux. So 1 micrometer central wavelength enables you to cover already quite a bit of this region, so you can convert towards mid-IR and also towards the XUV region. But it gets very difficult if you want to convert all the way towards water window XUV or even X-ray, and also in the other direction towards terahertz radiation. So a 2 micrometer central wavelength as a starting point turns out to be much more efficient if you want to go towards mid-IR, terahertz, or also the water window XUV region. And this is interesting because typically you only have access to these wavelengths if you go to a large-scale facility like a synchrotron. But now it is possible to have this on a tabletop setup in your lab. Our company develops lasers for quite a long time now, so we were founded 2009, and we've had a rapid development. We are focused on scientific systems, so the research market is our biggest market, and we are the technological leader for high power ultrafast fiber lasers in the world. And today we have 40 employees now, so you can see it was quite some growth over the last years. And we provide a large portfolio of products. So typically, as I said, 1 micrometer systems are our workhorse, but we also started setting up thulium CPA systems. And this is what I would like to talk about today, obviously. So what makes them special, we use large core fiber amplifiers. So you have a much bigger mold where you can amplify your pulses in. And this, of course, reduces nonlinear effects, and you can achieve higher pulse energies in a very compact and robust design. And also, if you combine it, of course, with chip pulse amplification schemes, you can address really high pulse energies up to the multi-millijoule range and very high peak powers in the multi-gigawatt range. What's different now, if you use a thulium-doped amplifier medium instead of an terbium-doped amplifier medium, you have some advantages, but also some disadvantages at first glance. So you have a very broad amplification bandwidth, broader than typical terbium bandwidth. But at the same time, you have a large quantum defect. So you have typically quite a strong quantum defect heating. But you can circumvent this if you use the cross relaxation, and this even allows for pump efficiencies up to 70% and higher. So, of course, there are some other challenges as well if it comes to 2 micron systems. So the suitable high power optics have to be available, which is more difficult, and you need high brightness laser diodes for the pumping. But if you handle all this carefully, and if you optimize the fibers and the experimental setting, the cooling concept, and all of that, then it enables you to achieve quite unique parameters. However, there's another challenge. It's the atmospheric absorption. So in the thulium gain region, you have lots of water absorption lines. So even propagation in air can become a problem at high peak powers and average powers. So it can destroy the beam quality, can also destroy the pulse quality. And well, if you manage to handle all that, you can set up quite a nice thulium system. So this is a system that I would like to talk about. We recently finished and delivered a few months ago. So you see this big box. It contains the oscillator, the stretcher, preamplifiers, main amplifiers, because it's a coherent combining scheme actually, and the combining. And then you have the vacuum transfer to the compressor, and the compressor is also completely set up in vacuum to prevent these water absorption lines from having impact on the beam and pulse quality. Yes, and this enabled an output of 200 microjoules at 600 kilohertz with 120 watts of average power and sub 120 femtosecond pulses. So this was the design parameters. And of course, this is also what we achieve. We use very good reflective dielectric gratings which had over 89% efficiency in total in the compressor, and a very high polarization extinction ratio of more than 20 decibel. The combining efficiency of the 4-channel combining system was also 95%. And we achieved an excellent beam profile. You can see it here at 120 watts of output power. And the beam quality was also excellent with an M² of 1.1. The pulse shape is depicted here. So this was at 200 microjoules and 600 kilohertz repetition rate. So you can see it was actually 111 femtoseconds, so below 115 femtoseconds, a bit better than the specifications. And this corresponds to 1.3 gigawatts of peak power. The spectrum was centered at 1940 nanometers, and you can see it's a bit, you can see a little bit these lines here, which originate from the water absorption lines. But still, the spectrum is very homogeneous, and you don't see a huge impact on the pulse. So you have a compressed spectrum shown here at 123 watts, so this is before the compressor. And the long-term stability is of course also very interesting, in particular for any application basically. So you can see here at an output power of 120 watts or more than 120 watts. I'm sorry, it was actually, the spectrum is of course at the output of the CPA behind the compressor. 120 watts and sub 150 femtoseconds, we had an RMS deviation of the average power of less than 0.15% over 90 hours. So quite a long-term measurement. And also the beam pointing was excellent, measured over 8 hours here, I think, in the range of 1 microradian standard deviation. This enables lots of applications, as I said. So you can address the fingerprint region, as we did here with an earlier version of the setup. And you can achieve a flux using this 2 micrometer system that is much higher than the flux of a synchrotron, actually. So not the flux, sorry, the brightness. And you can also use it to convert towards the water window XUV. So this is a very recent result from our partners at the Institute of Applied Physics, who used a similar system to achieve water window high harmonics. So you can see they got all the way up to 350 electron volts using a very compact thulium system. And of course you can use these water window high harmonics to do imaging, for example coherent diffractive imaging or pyrotography. Sorry, difficult word. And this is very exciting for many applications, also for pump probe setups. You can start at 2 micron and access different wavelength ranges than before. So we have these thulium-based platforms, and as I said, the big platform we offer now delivers up to 3 millijoules at 300 watts with 150 femtosecond pulses. And thus it is a great alternative to OPA towards 2 micrometer. It is more compact and simple. This, as I showed, enables you to go towards mid-IR. You can also use systems at lower power, of course. It depends on the parameters you want to have. For example, for these 100 milliwatts, of course you don't need 300 watts to begin with. And you can also do the water window harmonics, as I said. So the next steps, what we would like to do, based on the current system design, we will increase the energy further. So the system that we chipped, that I just showed you, will actually receive an upgrade soon. And we will increase the energy up to more than 500 microjoules at 200 watts of average power. And with a different system design, as I said, we can actually provide up to 3 millijoules and up to 1 kilowatt of average power. So we have the concepts and tests for that ready. And maybe the most exciting part, you can also go towards shorter pulse durations, and obviously for many applications a few cycle or even 2 cycle regime is very interesting, and we are aiming to achieve this using nonlinear compression methods, and very similar to what we did at 1 micrometer recently. So these are very recent results from the lab. You can see this is a few cycle multipass cell. So we actually used the fiber CPA system at 1 micrometer and in a 2-stage multipass cell compression setup. we achieved 1.05 millijoules at 105 watts of average power with 5.8 femtoseconds of pulse duration, and even were able to lock the CE phase. And also with very good long-term stability for a few cycle source, so below 0.73 RMS deviation. And of course the next step will be to do the same with 2 micrometer. But if you want to take a look at these specs first, there will be a poster about this on this conference as well. And yeah, as I said, soon the adaptation to a 2 micrometer input will follow. Thank you for your attention, and if you have any questions, we are happy to answer them, and otherwise enjoy the rest of the conference.